Well, this is going to be a little bit of a atomic theory and universal concept lecture for movement, space, light, and for my ideas on how the structure of the atom possibly could work, besides our current model that was given to us by Bohr. Uh, so the first thing I want to go over is movement, and if you nobody's really kind of thought about it in this way, but there's actually different types of movement. There's three different types that I have been able to ponder out, and I have them listed here. One is vibrational or resonance, and that type of movement is two-dimensional, where you can have something vibrating up and down or side to side or whatever direction it's going, it's vibrating, it's only going in a two-dimensional movement, side to side or up and down. Then you have another type, which is spin or rotational movement, and that's three-dimensional movement. You can have something that's a flat plane, like a flat disc, and you can start spinning that disc, and you spin it at the speed of light in place, then it can be pretty much like a three-dimensional object at that point. So you can have three-dimensional movement with spin. Now the third type is travel, where you can actually be changing location within a medium or volume, and that I consider a fourth dimensional type of movement. So
Okay, so now I'm going to go into the structure of the atom, and most specifically, I'm going to be going over the structure of the hydrogen atom.
if we think about how the structure of the atom must be, it must have like three parts of it, considering what we see in the emission lines of hydrogen and helium and such. Is they have to have some type of movement involved in their structure. They have to have some type of temperature involved, or creation of temperature, or some kind of way for it to heat up without not just coming out of nowhere. Like an aura of heat just arises with these atoms, and that just I just can't swallow that. And when it comes to physics, there has to be some sort of action reaction happening in the structure of the atom that's causing it to either heat up or stay heated and slowly lose its heat over time. It can't just get heat or temperature from nowhere. So that's what it requires. And the third thing is oscillation. Some sort of oscillation must be occurring to cause the light wave radiation that we see coming from atoms. We see the light that comes from glowing particles, we see them oscillating in waves of light that come out of them. So there must be those three things involved in the structure of the atom, without even knowing what it looks like or never seen an atom. But those three requirements must be in the structure. There must be some kind of movement, some kind of temperature, and some kind of oscillation that causes the light wave radiation that we see coming from glowing particles.
Okay, now I had a different idea at the time that I made this lecture, where I thought that the nuclei for hydrogen would be made up of four different sized particles, but I decided to change that idea into uh, four different overlapping orbits of groups of electrons that are orbiting at four different wavelengths inside the structure of the atomic atom of hydrogen. The electrons are orbiting at four different distances, and the higher the number, or the larger the orbit is, the lower the frequency is for the electrons that are going around at this wavelength. So electrons going around at this wavelength, the shortest nanometer wavelength, those electrons are orbiting at the fastest frequency or the highest frequency. The ones at the largest wavelength are orbiting at a lower frequency. Okay? And we can show this easily by just doing a quick little calculation of wavelength divided by, or the speed of light divided by wavelength equals frequency. So if we take the speed of light, which is 299792458, divided by 410 nanometers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 410 nanometers. That equals this for its frequency. Okay, so we'll do this now. Take another calculator, and we'll do this wavelength. So we take 299792458 divided by 0.12345678910. So 656.2 nanometers, and that equals this. See? So the higher the wavelength, or the larger the wavelength, the lower the frequency of the electrons that are orbiting it. So the ones that are at 410 nanometers are orbiting at this frequency, and the ones that are at 656.2 nanometers are orbiting at this frequency. This frequency is lower than this one, so the electrons that are orbiting at this wavelength right here are going around more times per second than the ones that are orbiting at this wavelength. And we have 4 different spectrum lines from hydrogen. We got 410 nanometers, 434 nanometers, or 439 nanometers, 486.1 nanometers, and 656.2 nanometers. Okay, so you have the one at 410 is at the lowest orbital distance. This one's slightly higher, so these ones that are slightly higher orbital distance. This one is at a higher orbital distance, and this one's at the farthest orbital distance for hydrogen. And because these electrons are all orbiting at the same speed, they're all moving at the speed of light. That's why we take the speed of light divided by these wavelengths equals frequency, because that's the speed that the electrons are moving. So, and if they're all moving at the same speed, but they're at different wavelengths, that means that the ones that are at the shortest orbital distance are going around more times per second than the ones at the highest wavelength. So this distance differential that the electrons are moving, like if this one, that the one at the lowest wavelength, they're moving at the highest frequency, is putting a temperature influence on these other orbital distances, because these ones are going around less times per second than this one. So because this one goes around more times per second than this one, it is transferring heat, or making the heat being retained by the distance differential of these electrons orbiting at different. They're not going at different speeds, but they're orbiting around less times per second because their wavelength is higher, or larger. The orbital distance is farther away. So the farther the orbital distance, the less times per second it goes around in a circle around the nuclei, the larger the wavelength, but they're all still moving at the same speed. This is what gives the atomic structure its ability to retain heat, because these are all negatively charged particles, and because you have 2 negative particles, they have a resistance to not want to go together. They repel each other, and because of this magnetic repulsion of the negative charge to another negative charge, this creates resistance and causes the electrons to retain the heat that they gather from any external source of energy. So like, say, a high voltage electric current. that we use to make the hydrogen atoms glow. And when we do that, we're causing these to heat up. The electrons are heating up in temperature. And when we take the high voltage away, the temperature is retained by the resistance of these electrons orbiting at different orbital amounts. The number of orbits they do is the difference between the number of orbits these are doing based on their different orbital distances and different size wavelengths cause the temperature of the hydrogen atom to be retained. It doesn't lose its temperature instantly because of the resistance that the electrons are receiving by the ones moving around more times per second than this one. So because there's this frequency differential, see, because this one right here and this one right here, because this one's moving around at less times per second. So if we copy this one, or no, we'll copy this one right here. Copy this, and we'll take this minus this one. So this is the frequency differential between this wavelength and this wavelength. So if we can figure out a way to take this frequency right here and figure out how fast the hydrogen atom loses its heat, then we can somehow figure out the connection that this frequency differential has between how much and the timing it takes for the hydrogen atom to lose its heat. I'm not quite sure how to do that yet. I'll have to brainstorm on it, but there's got to be some way to figure out how the rate that the atom loses its heat has something to do with the frequency differential that these electrons have being at different size wavelengths. And if I'll try to see if I can figure out that someday. Just I'll have to see how fast a hydrogen atom loses its temperature, and we'll have to figure out the frequency differential between each of these lines of spectrum, and somehow you can take the frequency differential and the temperature loss that it's getting per second, and you somehow connect the frequency differential with the temperature loss per second, and then you'll figure out how fast the hydrogen atom can lose its temperature based on how fast the specific frequency differential it has between its orbits. So the more electron orbits, or the more wavelengths there are in one atom, the more resistance that atom is going to have as its electrons orbit. And so the more spectrum lines that you see in an atom, the longer it can retain its heat for. Like, say if you heat up, say, a carbon atom and a hydrogen atom to the same temperature, the hydrogen atom is going to lose its heat faster than the carbon atom, because the carbon atom has more spectrum lines in it. It's got more electrons orbiting at more wavelengths within its structure. So it's because there's more wavelengths in its structure, that causes more resistance for them to travel. Therefore, the temperature drop that the carbon atom gets versus the hydrogen atom will be slower than the hydrogen atom. The hydrogen atom has the ability to lose its temperature faster than any other atomic structure that has more spectrum lines in it. The more spectrum lines that you see in the structure of an atom, the more resistance those electrons will have at all those different orbital distances. The more resistance, the longer it'll take to lose its heat, because there's more resistance. The more resistance, the longer it takes for it to lose its heat. Okay, so I have a hunch that the corona around our star, and probably around other stars, will have something to do with this retaining of heat by the structure of the atom. Uh, when the when our star is giving off its light energy out into space, there is free floating hydrogen atoms and helium atoms in the atmosphere of our star. And as the light waves interact with those free floating atoms that are in the atmosphere of our star, it causes them to heat up. And the heat that we see in the corona is far greater than the heat that is coming from the surface of the sun. And this is not very well understood. And I have a hunch that this atomic structure that I just proposed of the resistance of the different orbital distances causing resistance to the heat temperature drop has something to do with the corona and why the temperature of the corona is so much hotter than the surface of our star. Because the hydrogen and helium atoms around the star in the atmosphere of our sun is gathering temperature from the light radiation that's coming from our star. It's not directly touching the surface of the sun, but because it's receiving all that energy from the radiation that it's putting out, that causes the hydrogen atoms, the free floating hydrogen and helium atoms in the atmosphere of our star to heat up. And the the temperature of the hydrogen atom must be able to rise like to very dramatic temperatures, to millions and millions of degrees. That's why we have a corona around our star that is very, very hot compared to the surface of the sun. And that's why also when we look at stars that are much larger than our sun, that have a much more um, have more atomic nuclei in them, like the blue giants and all those really large stars have not only hydrogen and helium in them, but they also um, fuse what is it? Carbon, nitrogen, all the noble gases that are created in the fusion of big gigantic stars. They are all much hotter, and the coronas are all a lot hotter because of this resistance of their electrons in their atomic structures in the atmosphere of these stars. Like the atmosphere of the blue giants and the atmosphere of the very large stars, they have free floating atoms in their atmosphere. And we only have hydrogen and helium in the atmosphere of our star. But the blue giants and the much larger stars, they all have those other um, more dense atoms, the noble gases, the carbon, nitrogen, all those heavier elements that the larger stars create. Those uh, those all have more spectrum lines in them. So therefore, the heat that is retained by the structure of those atoms will be much greater, and they'll lose their heat much slower than our star. This is the reason why the coronas around large, gigantic stars are much hotter than our sun, because the atomic structure of the atoms in their atmospheres are causing more resistance. Therefore, it's causing them to heat up much more. This this atomic structure makes more sense to me uh, based on the temperature differentials of the large stars versus a star like our sun, because we only have hydrogen and helium in the atmosphere of our star. And hydrogen and helium are the lowest structure, there's the least amount of spectrum lines in hydrogen and helium. Therefore, those atoms will retain heat and lose their heat the fastest compared to the large stars, because the large stars will have in their atmosphere atoms that have more spectrum lines in them. And the more spectrum lines in the atomic structure of the atom, the more heat they can retain, and the longer they can retain that heat that they lose over time. That's why that's my hunch when it comes to the structure of the atom, and the reason why we see temperature differentials that are so much larger in the coronas of stars than we see on the surface of stars. because the radiation energy that is being emitted into the atmosphere of these stars have free floating atoms in their atmospheres, and the more dense atomic structures in the atmosphere of these stars, the more spectrum lines that are in them, the more resistance, the more heat they can retain, and the longer it'll take for them to lose their temperature over time. That is my hunch for how the coronas work in stars, and this is my first uh, section of my lecture when it comes to atomic theory, light, movement, and universal concepts of the universe.